Good morning, good afternoon. Thank you to be at this third presentation of our MicroNIR learning series. Today we will talk about MicroNIR application for blending monitoring, especially for Tumble Blending. As you know, because you have already attended maybe the first two sessions, this is a part of a more extensive series. We started with raw material. Last week we discussed of the granulation and dry monitoring. Today is the day for blending. Next week we will touch base on the compression, tablet compression and tablet coating, and we will end up on the 14th of May with a new introduction of a new hazard location product. This is the agenda for today. There is a small product introduction and company profile. We will go directly to the Tumble Blender monitoring, and afterward Christina will go through the moving block standard deviation, and she will also show some example. We hope to stay in 45-50 minutes for the presentation and leaving the final 10 minutes for the question and answer. Today's speaker, I introduce myself. Probably a lot of you know us already. I am Emiliano Genorini, based in Italy and account manager for the MicroNIR product line for the EMEA and for the Latin American area. Christina is a MicroNIR field application specialist, and she will spend some more word about herself later on.
Yes, good morning everyone, also from my side.
Couple of words regarding our company. VIAVI is an American company. We are divided in two business units. One is called NCE, that is working on the telecommunication side, and the other one called Optical Security and Performance Product. That is where the MicroNIR product line is inside. Actually, inside the OSP business unit, we are working into different marketplaces. We are active in the consumer electronic, where we provide filter for mobile phone and for computer, government and aerospace. We have a big part of our business on the anti-counterfeiting product for the banknote, and we provide also special solution for automotive. MicroNIR is inside the spectral sensing group. This is important to understand a little bit regarding the MicroNIR product line. What is our vision? The vision is enabling a smarted world. Enabling a smarted world working on 4 cardinal points. The miniaturization. On the left-hand side, on top, you see the original MicroNIR, the one that is called 1700 ES. Is a very teeny and small and compact MicroNIR that is basically less than 5 centimeters and 64 grams. In the other position, you have the on-site and the PATs system U and W. The W especially would be the protagonist for the presentation today. But you see immediately in the opposite side of the miniaturization, you have a performance. Here we are talking about instruments that are designed to be professional tools, are not designed to be a consumer spectroscopy device. Means that the performance are really good for monitoring a process or to be around with the handheld device like the on-site. Is also important in terms of future, the affordability. Affordability doesn't mean lower price in the market, but mean good price fit for a specific purpose. And the connectivity. The connectivity can be read in 2 different ways. One way is the connectivity in the cloud, especially for the handheld device, especially outside of the pharma market, or connectivity into the pharmaceutical market can be read as in connection with the OPC in order to exchange data to an HMI and to have a completely automation of the sensor inside a blending machine in this case, or it could also be a air shear mixer or a fluid bed dryer or whatever you want. What is the technology inside? The technology is a VIAVI technology called linear variable filter that is the acronym is LVF and is a one-dimensional continuously vary bandwidth filter. The filter is fabricated on glass using hard, dense, and stable inorganic material for a long life and environmental stability. It came up that is a very compact part. You can see is very small. It's like a piece of rice. And this enables us to have a very small and compact and stable device. This filter has been developed for the NASA mission you see here, and is say inside the MicroNIR devices. You can see here a cross section of the MicroNIR, and for sure the fact that the linear variable filter is so small and is directly glued to a gas detector enable us to have a very compact design. You can see that here you have the linear variable filter, here you have the detector, and you have two tungsten lamp that are emitting the light that goes to the sample and come back through a collection optic through a specific special light pipe. The distance here are very small, and this allows us to have an incredible level of signal to noise. We are talking about more than 20,000 to 1, actually around 25,000 to 1. This enables us to move from a traditional NIR optical bench to an NIR sensor. On top of this, we have no moving part. So no moving part means that we have no possibility to disalign, long-term stability, 100% transferability between the units, and also that there are no fiber optic, so nothing that can be damaged or wear out, and is almost insensible to the temperature variation. Other 2 points before moving to the next step are related to the lamp. The lamps, they have a lifetime of more than 40,000 hours. Okay, that is an incredible long time that minimize the maintenance cost of a device. The maintenance cost of a device are also minimized because we do not use any laser like in the FT system. So like this, there is one piece less that you need to consider in terms of replacement of consumable over the time. We provide different kind of solution, starting from the instrument that are anyway accumulated from the fact that they are very small, compact, and light, that are provided as an OEM product, but also as end user product. In case of end user product, we provide a comprehensive solution, including accessories, special flanges, special extended probe, different kind of adaptation, and so on, and software. Software is a very important point because it's 21st CFR Part 11 compliance, is USP 1119, and we are working on the 1856 new version of the USP, and that actually will be valid from tomorrow on, and the AP 2240 for the validation. The software has an embedded package that allow to apply chemometric treatment and chemometric modeling from principal component analysis, moving block standard deviation, spectral match value, and NPLS. In case that you want to do more, the software is compatible to Unscrambler, Simca, and Solor. This is our baby, is still the smallest NIR in the market, is the 1700 ES, that is actually now dedicated basically to academic purpose, but the functionality are exactly the same on all the other devices in terms of optical performance, and is enough to connect this piece of hardware with a USB cable to a computer and get a spectrum. Here you have the IP67 and 65 and 67 product line, the handle device, the on-site that we treated quite deeply during the raw material identification, the PATU and the PATW. The PATU is normally used for static application. We saw last week the possibility to use the PATU in granulation and drying process. We will see next week the application of the PATU in the tableting and in the coating phase, and PATU, sorry, and the PATW is the same hardware but with a wireless connection, Wi-Fi connection with a battery that can be attached to a Tumble Blender and could rotate together with the Tumble Blender. It's important also to see that the device is wireless, but it can also be connected with the Ethernet connection. It has a lithium-ion battery with a working time more than 8 hours, and it has multiple trigger options, including the possibility to use a specific triggering for the Tumble Blender. These are the hazard location product, so ATEX and NEC, the PATU and the PATW, that basically are the same device of that we saw before, PATU, UX, WX, but done for hazard location, and here you can see the full certification label for explosion proof. Process analytical technology. This is where we find the right habitat for our devices. First of all, because process analytical technology means process understanding. We need to understand the performance and the quality attribute of the material that we are using in our production. And I like especially these two sentences, especially the second one, where we say that the quality cannot be tested into the product. It should be built in or should be by design. So here you have the link, the two articles that you are free to consult later. But this is a very important point, a very important slide, because here we have on top our raw material, we have our process and our tablet at the end. The classical thing that we try to do is to keep as more as constant the ingredient, the raw material, and this is correct. We can identify the raw material, we can only buy from a validated supplier and so on. But if we keep the process constant, it ends up that the output will be for sure variable, because the raw material, even with all our endeavor that we can make, are variable by definition. So if a process is constant and not known, it ends up that the final product will be variable and unexpected. The aim of the PAT is to know the process and to understand the experimental domain where the critical attribute allow to have a constant process. So we are moving the focus from the raw material to the process. We are not scrutinizing the raw material, or better, we are scrutinizing for sure the raw material, but we want to put the focus on the process in order to know the process and to understand how a variability in the raw material can impact the process in order to have a final product that is constant. This is something that I really like because in the traditional approach, the process is developed, frozen and validated. That's it. The only way to keep under control the process is process safeguarding using SOP, using training, and so on. And the quality is tested just at the end in the laboratory. The PAT approach is pretty different because here the process is, we can consider the process constant anyway, but during the developer phase, the process is analyzed deeply in the details with online and inline analysis, and is the process that is, I would say, well understood and continuously managed in order to keep under control all the possible critical attributes. And here there is for sure statistic and multivariate analysis that are playing a key role into this. Obviously, I showed this slide already last week. The cost of quality in the traditional approach, quality by test, it's very low in the beginning and it goes up dramatically when you get something wrong in your production. In the quality by design, the costs are for sure higher in the learning period, in the beginning, in the R&D phase, but afterward they are constant forever along the product life cycle. Where is possible to use an NIR sensor for doing process understanding? Raw material, blend uniformity, granulation, loss on drying, compacting and tableting, everywhere. And what VIAVI is providing, a hardware and an analytical interface toward the equipment, but from the mechanical side, but also the possibility using the OPC to interface the result and to transmit the result to the HMI, and in this case we work with OPC UA or DA. But let's go now to the most important part of this presentation, that is the Tumble Blender monitoring. In the pharmaceutical production, the tablet are really important. It's for sure the major, let's say, is the most popular pharmaceutical form. And one of the key points is to be sure that the process is homogeneous. But not only that the product is homogeneous. And when I say the product is homogeneous, I mean APIs and excipient together. The traditional way to evaluate the homogeneity of the product that we mixed is at the end of the blending, stop the blender bin and with the sample teeth take out, for example, 10 samples following the ICH guideline. Afterward, the samples are delivered to the laboratory, to the quality control laboratory, that they start using that they analyze using HPLC, UVs, and whatsoever. This is the traditional approach. It's good. Yes, this is what we are used to, or better, we were used to. The problem in doing this is that basically it's not possible to monitor in continuous the product. It's time consuming for the laboratory. The operator is exposed to dangerous substance, and the blend product is exposed to the environment, especially when we have very active API. This is really not pleasant. But the real problem that we have to face is the same, because when we take our sample teeth and we go inside into the product, we create a hole. Once we have this hole, obviously is not remaining for a lot of time, because depending on the different particle size inside the blender is immediately filled by the finer particles. Okay, and this is a clear problem, because if you repeat this sampling for 10 times to take out the sample that you bring to the laboratory, you achieve two things. The first thing is that your blending is heavily damaged by the sampling. So it's up to you what you want to do, but it's for sure not the product that you had before the blending. And this is clear stated in the article that is in the right-hand side. And also that the information that you are getting are not representative of what you have inside your blender. So this is a clear need to play the game in a different way. How can be done? It can be done attaching to a blender a MicroNIR sensor, for example. In this case, we have created a special attachment that we provide in our offer called lead mount kit. Basically, there is a sapphire window. The device is never in direct contact, and there is a trick clamp, never in direct contact with the product inside. There is a trick clamp for an easy connection of the device, and the MicroNIR, as I said in the beginning, has a special trigger that is able to acquire a spectrum when it's upside down. The advantage of having a small device that weighs less than 1.5 kilos, including the battery, is that you can move from a laboratory blender to a big production blender, just clamping the device. So this is a very flexible way to work. I want to spend a few seconds also on the gravity sensor. Okay, this is quite important. The software has a function called the trigger mode, where you can select the gravity mode. Actually, you can select the trigger with the push button, you can select the trigger with the proximity sensor, or you can use the gravity sensor. You see on the left-hand side that there is the rotation, okay, and on the top, that here is designed with a red line, the device during the rotation on the upper part, the MicroNIR is an inactive mode, so it's not measuring. When you go from 9:15 to 8:45 to 9, so the two positions here and here, 9:15, sorry, 12, 3 o'clock and 9 o'clock, sorry for the mistake. So here in this part, in the upper part, is not working, is inactive, and is active when is on the lower side. But normally the flow of the product inside the bin is not from 3 o'clock and 9 o'clock, but is in a narrower range. So we need to narrow this angle. How this angle is managed using a delay time from 3 o'clock, or if you work clockwise or anti-clockwise, from 9 o'clock, in order to get the measurement in the 6 o'clock position. One of the advantages of working like this is that we can also play with G1, G2, and G3, that are the gravity parameter, that help us to configure properly the trigger, even if the MicroNIR is not rotating on a plane, but is rotating, let's say, in front of you, or with different angles. What is important and why the MicroNIR is important? First of all, the formulation lab. Formulation lab is important because there is no sampling required. Real-time feedback. We can optimize the blending time. We reduce the quality control effort because for sure they are not happy to get a lot of samples to analyze because normally the process validation and the formulation are somehow independent from the quality control laboratory, and is important because we can apply a quality by design where the quality is built into the design of the product that we saw as a better as a lot of advantage compared to the quality by test where we do the quality control just at the end of the process, and we can properly define the experimental domain. But the NIR on a Tumble Blender is also important in the real production because sampling is not required, real-time feedback is not required, but we can do a continuous manufacturing as well, and we can keep under control continuously our processes. And this is what I put on bold, is very important, the difference between process validation, where we analyze 3 batches and we crystallize everything, and the continuous process verification, where all our batches are really analyzed. And this is really the final aim of the NIR connected to a blending system. What can we see, or better, which are the parameters, the critical attribute that can impact into the blending? The rotation time, the API concentration, the excipient, particle size, blender capacity, rotation rate, filling level, a loading method. This is an example that I really like, where you have different graphs, where on the X you have rotation number, so the time, and on the epsilon, so on the vertical axis, you have the moving block standard deviation. What the moving block standard deviation is the variation inside our spectra. Christina will touch base with you later on this. You see that, for example, here we see that we move from 5 liter, 10 liter, 40 liter bin, and the mixing, the blending is having different profile because it's behaving into different way. Same, this is important for the scale up from the R&D to a production. Here is just from 5 to 40 liter, okay, but you can imagine this one from 25 liter to 2000 liter, and is the same. Furthermore, you can play with the filling level, and depending on the filling level, you could have different profile. Okay, you can have 60%, 75, 90% of filling level. You can play with the rotation speed. Especially in the beginning, I thought that if I was rotating, we're rotating faster the blender, the results are better. Actually, no, the results are better if you find the right speed to blend your product. And the same is the way that you are loading the ingredient inside. You see this one on the button here on the right hand side. You can, let's say, load the product in a certain sequence and you get a result. If you put, let's say, in an asymmetric way, off-centered with spot the product, you get another result. So this is helping you to understand how your project behaves when the critical attributes are changing. How to validate the NIR result? This is a key point. First of all, the first thing that we need to forget is the parallel between NIR and HPLC. On top, before starting, we saw that taking a sample, the sample is destroying the blending and is not representative of what you are doing. So this is not a good idea. Second point, the NIR is a spectroscopical measurement. So we measure the API and the excipient. The HPLC is just measuring the API. So it's not the same. The HPLC is measuring the API concentration. The NIR is measuring the blending, the overall, I would say, mixing of the product. We can use two different kinds of algorithms, the moving block mean or the moving block standard deviation and the principal component analysis. But both are unsupervised methods. So when I put my threshold, if I go back to this slide, when my product is blended in a proper way. So with the moving block, or eventually even with the principal component analysis, I can are nothing, even if I use the F-test that is 100% sure that the product is mixed. So there are two options. Option number one, my preferred one. We compare multiple batches profile and we see that are coherent or not each other. The option B that is becoming somehow interesting more and more is that you check that indirectly the tablets are homogeneous because it's something that you have any way to do. Okay. In fact, you see that normally the quality control must take 10 tablets and every hour during the compression and check the variability inside to verify the homogeneity. Obviously, there is an original sin here that is that in the option B, you are measuring tablet versus the product. The advantage is that you can make one batch, you have a tablet, you check that that batch, the tablets are good, and so you can set properly your threshold. You can somehow verify your threshold. This is an example that afterward Christina will show more in the details. No, is a mixing. You have different color that are basically showing you the temporal, the time variation. Is API and lactose, original spectra pre-treated. You see that is a pretty nice variation, and the in this case is not the moving block, but is the percentage area of the spectra, but is very similar. Okay, you have the mixing phase and the end point. What has been done here? It has been done that we overlapped 3 batches, and we saw that after 310 rotation, the result of the 3 batches are pretty coherent each other. So we can claim that 310 after 310 is good. You saw probably that around 200 rotation, there is another minimum point there, and you see that anyway, after 200, it goes up a little bit, it comes down, okay, and it stays down forever just after 310. This is the reason why we prefer to define the endpoint at 300 instead of stopping the blender at 200 rotation. But the thing that he captured my attention was the loading. The funny stuff is that the loading of the principal component 1 was basically very similar, and is the where is the green and the blue. The green is the PC1, and the green is the lactose, and the PC1 is the blue. Okay, you see that they have a maximum at the same wavelength, and also so means that PC1 is driven by the lactose content, and the PC2 is driven by the API, in this case, the omeprazole. When we plot the PC1 versus the PC2, it's interesting to see that in the beginning, there is a movement from the right to the left on the PC1, that is exactly the lactose, and afterward, we have only later on, only afterward, we have a movement from top to the bottom on the PC2, that this is the variation of the API content. So basically, like this, we can split between the two principal components, understanding also a meaning on what we are blending. Last but not less important example, okay, is this one. This is a API with a very low concentration, 0.1%. You have the pre-treated data, and I mean, you don't have it here, but at around this point, 11:45, 40 something, here where I have a mouse, this is where the API is absorbing. And if you make the pure API, you get exactly the peak here. The customer here was quite skeptic in terms of possibility to see such a low dosage of API. And so we try to spike some concentration, and we built up a PLS calibration curve that was done. I want to clarify because I don't want to have this question later on. Basically at line. So the PLS here is done at line, putting a small amount of sample in a beaker and mixing up by hands with the let's say different API concentration. You see that the concentration is quite nice, or better, the correlation with the concentration is quite nice. And you can see from the R square and also for the error that is, even if we are talking from 0 to 100%, the error is quite low. But the customer was not happy about that, because the target was to demonstrate online that online was possible to see the 0.1%. One of the assumptions is that build a quantitative calibration for a blending is maybe not the most bright option. And I also tell you why. First of all, because you don't probably need to know the quantification, the quantity of the API, because in the dispensing area, you are weighting the amount of API that you are putting into the bin. So you know already, and the target is not to know that is 0.1 or 0.2%, but is to know that is homogeneous, distributed into the product. It's a little bit different, the target. And also because it's very complicated to create models, PLS models, that are good online, because you have a rotation, because, as I said, you have a sampling effect, and so on. It ended up that we had to find a way to demonstrate that it's possible to see such a low concentration. Here we made A1, A2, and A3 that are blending with the API inside, and P1 and P2 that are blending only of the placebo, so no API inside. You see that the two placebo are changing in this direction, okay? The API, sorry, the active blending is moving in the opposite direction. This is the clear demonstration that there is a separation between the process trajectory of the placebo and the process trajectory, the blending process trajectory of the real product. Saying that, considering that they are not overlapped means that we are able to see the API during the variation. The demonstration, final demonstration, is this one, where we projected the placebo. You see in blue is the calibration, so the active one, okay, so the variation on the active one, and in green are the projection of the placebo one on the active one, the placebo one, sorry, the placebo 2 on the active one in the second case. You see that the two groups are separated. There is just a minimum overlapping. And this is, again, the clear demonstration that you can monitor such a low concentration. Obviously, to monitor something that is 1% or 5% is very easy. When you have to go down to 0.1%, you need to do something more, going and diving more in the multivariate analysis. This is the last slide from my side. I make Christina presenter that she will drive you in the software side with a nice hands-on. I see that there are some questions. As last week, we will reply to all the questions at the end of Christina's session. If we will try to select the most interesting question. If there are some other questions that we cannot reply because it's too late or are too complicated, we will take it in a separate way, and we promise to reply to all the possible questions. Christina, you.
Yes, here I am. I think that you can see my screen.
Yes.
Okay, great. So good morning or good afternoon, or I don't know good what, to everyone, depending on your time zone. So for the one of you that already attended our seminars the last weeks, this is something already know, but my name is Cristina Malegori, and I'm in VIAVI doing the work of the MicroNIR field application specialist. And I have the possibility to do this work thanks to a collaboration between VIAVI and my research group. I have a postdoc fellowship in the research group of analytical chemistry and chemometrics in the University of Genova in Italy. And my research activity is just focused on NIR and chemometrics. And what is chemometrics? Is the way in which we try to understand the fingerprint signals that NIR give us and understand the information that is behind these complex signals. But what we want to do today together is something more practical, and I will keep the theory really, really light. If you remember, in the last weeks, I tried to acquire some sample together with you for both the raw material identification and the drying monitoring. But today was too hard to have here at home with me a big blender full with powder and API. So unfortunately, imagine that I already acquired my spectra. I have my spectra in the computer, and we will just use together the MicroNIR Pro software. So we cannot do a really hands-on session due to our situation, but imagine that these spectra were already acquired with a PathW, and as Emiliano already showed you before. The case study is blending monitoring, is a binary mixture of lactose and 5% of API. The aim of our work together is knowing how to follow the blending process, and we will do it using the moving block approach. As Emiliano already anticipated, we can use also PCA projection, and we have certain conditions in which PCA projection is an advantage in respect to moving block approach. We saw PCA projection last week, and we will focus today on the moving block approach. But thanks to the approach that we will see together, we can also determine the endpoint. What is the endpoint? The endpoint is the moment in which our mixture is as homogeneous as possible. So we cannot reach a system more homogeneous than the one that we determine in the endpoint. When we decide an endpoint on a specific blending, on a specific mixture, we can then use that blending for a future threshold for all my other blending of the same mixture, because the fingerprint signal of that mixture will remain the same one a long time. What is the moving block method? So in the family of the moving block methods, we have mainly 3 approaches, and they have to be used together, and one can help the other or can be more efficient in some situation and not in other situations. All the 3 approaches are available and are implemented in the MicroNIR Pro software, and we will practically see all the 3 approaches. But let's see what is the difference between them. We have the moving block standard deviation. This is the most common one between the moving block methods. Is a really sensible approach because it's able to assess the uniformity of a mixture also when we have really small variation. So this approach is suitable for detecting small differences a long time. But sometimes the ability to detect small differences became too much. So we are seeing something that we don't want to see. So in this case, we need something more robust, suitable for more complex approaches, and this is the moving block mean. And in particular, the moving block mean is suggested when you have a lot of ingredient inside your mixture and with different particle sizes. So the different particle size can create a little confusion for the moving block standard deviation, while the moving block mean can answer to your question in a more robust way. We have also the relative standard deviation. This is another really sensible parameter because we are measuring the percentage ratio between the moving block standard deviation and the moving block mean. So it means that we are looking at the variability between each spectra and the mean of the block. So this is a concept that will be quite useful to detect faults inside your blending process. Something that Emiliano already said is that when my blending is finished, when my process is finished, when the charts that I can plot from the moving block standard deviation, the moving block mean, and the relative standard deviation are going down, 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 reaching a plateau. Okay, so the differences between the spectra that I'm measuring are becoming small, 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 and smaller. So it means that I'm reaching the endpoint. But remember, again, that the endpoint must be validated. And of course, we can trust these moving block methods, but we have to confirm what we obtain from this data processing. Entering a little bit more in the algorithm, we can see that we have to choose the dimension of a block, the moving block method, so we need to define this block. And what is this block? Is the number of spectra that I want to consider as a unique block, a unique boxcar. So this number is something that you have to decide knowing your process and knowing the macro and micro changes that you have inside the blender. When I have decided the dimension of the block, this block will move exactly like a boxcar along the profile, along the spectra that I'm acquiring. So it's a small group of spectra that is changing a long time. And what is happening is that I will continue considering 5 spectra, for example, let's use 5, and I will discharge the first spectrum when a new one is acquired. So the older one is rejected and the new one is included inside the block. For every block and for every new acquisition, I will calculate my 3 parameters. So the moving block mean, so the mean of the block that is moving, the moving block standard deviation, so the standard deviation inside the block that is moving, and its relation as RSD percentage. So we can see that mainly what we are doing is measure the variability along the process. The lower the variability, the less heterogeneous my mixture is. When we have to define the endpoint of our mixture, sometimes we need help from statistics. And in this case, we have the help of the F-test. The F-test, for the one of you that are familiar with statistics, is something really common. That is the Fisher test. In the Fisher test, what we are doing is to compare the 2 variants of the 2 blocks. So you can see that in the slide here, you can see that the blocks are not contiguous. So I'm not changing just one spectra inside the block for each acquisition. But in this case, for performing the F-test, I need independent blocks. So it means that the first, for example, 5 spectra are used for calculating the variance of the first block. And then for spectrum number 6 until spectrum number 10, I will create the second block and I will calculate the variance of the second block here. And then I can compare the variance of block 1 and the variance of block 2. When I have this F calculated, I can compare it with the F tabulated. The F tabulated are numbers that Fisher already done for us, and so we will just compare our F, that is represented as a small dot along this line, with a threshold that the software is automatically given to us. So when the dots falls down the limit, it means that our process is not changing anymore. It seems really nice to use just the F-test and not to do the validation strategy that Emiliano explained us, but we have to forget completely to use the F-test as a rule. The F-test is just a help for taking your decision. And we will see right now how to use the F-test in comparison with the moving block mean to decide our real endpoint. We have also some interesting stuff inside the software that I will call advanced strategies. They are based again on the moving block methods, but what I can do is to perform the moving block on one or multiple selected region. For example, I know that I have inside my mixture 2 API that have a strong peak in the NIR region. So I can follow API number 1, focusing a moving block on its peak, and following the API number 2 with another moving block. But for doing this approach, I need to know the absorption and the spectral profile of my pure ingredients. And this is something that we can easily do in our plant, and it's an information that will help in understanding our system. Another stuff that it's not so easy to find in commercial software, and that is implemented in the MicroNIR Pro software is the performance of moving block onto the PCA profiles. What does it mean? It means that I use PCA, principal component analysis, as a compression method. So to discharge the information that is not interesting and just resume the information, the variability that it's for me nice. And then I perform the moving block strategy onto this profile, not directly related to the spectra, but directly related to the PCA scores. This is something a little bit more advanced. I don't think that we will have time today, so I will go rapidly in the hands-on session. So I will open the software. This is the MicroNIR Pro software environment. What I have to do today with you is a moving block model. I click on New and I create my moving block model for blending. Now I have to retrieve the data on which I want to perform my analysis. These are the data. I click on retrieve and I have my fantastic spectra. Here you can see that I have the advanced option on the number of region and on the method apply to spectra or apply to PCA score. We will continue easily applying on spectra and I will apply just a simple first derivative on my spectra just to enhance the peaks. And now I will go a little bit faster than what I was expected, but trust me, we will use it on a boxcar long 25 spectra, and I click on apply. When I do this, you can easily see that I have this line with a high standard deviation at the beginning, and go ahead, I continue going down, going down, going down, reaching the minimum of the standard deviation around here. But if I want to see also the moving block mean profile, what I have to do is to go on endpoint criteria and click on both moving block and standard deviation and moving block mean. Here I have also the possibility to click on RSD, but this is not interesting for our example, so I will be focused on this. This is moving block standard deviation profile, and this is moving block mean. I really nice this. I consider really nice this profile because it go up and then it slow down until a constant value here. So what I can easily do is to set manually an endpoint, for example, on this moving block mean that I really like. I will set the parameter that I check this morning that were right for this example. Trust me and we will see why. I save my limit. And here in the moving block mean, I can see that the red dot means the blending is not ready to be opened, and the green means now the mixture is okay, cannot be more homogeneous than now. So this is my green point, the point in which I have to discharge my blender. If we want to see the advantage of using the F-test in combination with other statistical approaches, we have to perform it on standard deviation because the F-test works on variance, so I can apply it just on moving block standard deviation. I have just to click on F-test and then click on apply. You can easily see that here all my dots are out of the limit, then I go out, but I don't have to trust because I go out again and I go out again and again. So if I look at the moving block mean, I can imagine that from spectra around 200, my blending is okay. But remember that the mean is less sensible in respect to the standard deviation. So if now I look at the standard deviation, I have still something out around 200. So I will wait around 220 to discharge my blender. So I'm sure both from the point of view of moving block mean and from the point of view of moving block standard deviation. And this is what we call consistency in chemometrics. And this is something that when you are doing blending, you have to try to find. And also overlapping different blending made with the same mixture will help you in understanding your right endpoint. I think that I have finished the time, so I will open a small session of question. Emiliano, if you agree. There are other stuff regarding PCA and so on, but today we didn't have time to do this. But if you are interested in knowing this advanced strategy, feel free to contact us.
Thank you, Cristina. It's my fault that I was a little bit longer than my expectation. But anyway, for software explanation, we are really happy to reply later. You have here the contact information for the MicroNIR that you are really free to contact it anytime or directly Cristina and I. Just a couple of information. All the things where the presentation and recording will be sent to you by tomorrow, and we are uploading to YouTube the video of a session that you can see whenever you like. As I said at the beginning, we want to reply to all the questions personally, and this is a commitment that I'm taking. I just select a few common interest questions to reply online, but as I said, we will reply to everyone. First of all, we have a question regarding very important point, transferability between different units, and this is important because all the MicroNIR that are based on the linear variable filter are exactly the same. So is a, let's say, 100% possible to transfer straightforward the calibration from one device to the other one. Another question, maybe Cristina, you can take this one, is if it doesn't make any sense to select individual wavelengths versus a overall region. What do you think?
So this is a nice question for a chemometrician because we think multivariate, so we don't want to use a single wavelength. And what I can tell is why single wavelength. If these wavelengths that you want to select are so important, they will arise also if you will take the whole spectra. Is different if we are speaking of selecting a region of an interval of wavelength, not just one wavelength. And it's different because I'm taking into account a specific chemical information and it's the knowledge that I have before. So I know that my excipient has a strong absorption in this part of the NIR region, and I'm not interested in the behavior of the excipient, so I will discharge all these wavelengths. But the other, it's better to use all the wavelengths together because the NIR spectra is something really complex and some information that cannot be easy to see by naked eye maybe are hidden behind big peaks, but chemometrics and multivariate techniques are able to detect this variation. So my suggestion is to use every time the whole spectra if you don't have specific chemical reason to select wavelengths or region of wavelengths.
Another question for you, Cristina, is it always necessary to use the PCA or the moving block is enough?
It is not necessary to use PCA. For example, if you have a binary mixture, as in my case, I can apply PCA, but I don't really have an interesting information from PCA. For more complex mixture, and also when I have different particle sizes, maybe I can use PCA, let me use this term, as a filter for filtering out the information that are not interesting and keeping the chemical information that inside the data, the most important part of the variability, as we said in chemometrics. But PCA is the second step that you have to do if a simple moving block is not working. Something that I say every time, and Emiliano already know very well, is the fewer the better. So if a simple approach as moving block works, let's continue with it.
Okay. Another question is, if I have, let's say, multiple component that I'm mixing with other multiple component, what is going on? I take this one because that is a little bit cryptic, no? But I mean, let's suppose that I have a premix where I put together A, B, C, and afterward I have another ingredient that I add later on. So here we need to go back to the basic of the moving block standard deviation approach. Here is important to see a variation of the fingerprint, and the fingerprint can be a fingerprint of a single raw material, or can be a fingerprint of a very complex mixture of ingredient. But anyway, what is important to see is the relative variation of a fingerprint. So this is what we consider really as an important stuff, independently from how many components we are mixing together. Important is to see the variation of this product all together. Another interesting question is how can be defined a threshold, and I think that Christina mentioned that or you trust in Fisher test and in Mr. Fisher, or you try to see if multiple batches are coherent one to the other. As I said in my presentation, you overlap multiple profile, and once you see that multiple profile are, let's say, landing at the same rotation number, means the same blending time, means that this is your threshold. You cannot mix better than that point, even if you go ahead. The risk, if you go ahead, is to create segregation that from time to time it could happen.
I think that we have Maurizio Valleri that raises his hand. Maurizio, you can confirm, open your microphone if you can, or I open your microphone.
Send us a message and we'll reply.
Okay. Thank you. I want to know if it's possible to connect this apparatus that we have also with a system to stop the blend when the blending is ready.
Absolutely, yes. You have to use a plugin called OPC UA and DA, and you need to connect us, Maurizio, with the Blender supplier, because obviously we provide the way out of our signal, and afterward we need to discuss with the Blender supplier to define the integration. But basically you have 3 different options. One option is that you transfer the signal stop or not stop based on a logic that has been implemented into the MicroNIR Pro software. The other option is that you broadcast, this is the right word, the moving block standard deviation continuously, and the HMI or the Blender decide when it's below a certain value and it stop. so is the HMI of the Blender deciding what to do, or even worse, you can transfer through OPC the whole spectrum to the computer of the Blender, and afterward you can process that data directly there without even our software. So there are different options. If you want, send me a mail or give me a call that we will go into the details.
Okay, thank you.
Emiliano?
Okay. Hello?
Okay, yes, now I can hear you.
I think that we can stop here for today. Again, thank you very much to all the staff and to all the attendees. We really hope to see you again and even more next week when we will talk about tableting and coding.
Thank you.
Thank you.